Good morning, everybody. Today I'm going to discuss systems composed of indistinguishable particles, and especially I want to go into the discussion of bosons and fermions. Now, if we consider n identical and non-interacting particles an ideal system, we can write the Hamiltonian of the system as follows in terms of individual or sum of individual Hamiltonians for n particle system. This enables us to write the Schrödinger equation as for the system as the following. Now, you have to keep in mind that you have n particles in your system. Now, a straightforward solution may have the form some multiplication of single particle states. Now, these are the solutions of that Schrödinger equation corresponding to that Hamiltonian, individual single particle states. Okay? So, you have to understand the system wave function as single particle states. So if you want to distribute these n particles, you have to put them into these single particle states, one after another, till you have n particle system. So you can talk about distribution of these particles in these states, single particle states. Okay? Now, the total energy of the system will be sum of individual energies of particles. Okay? And these U's are going to satisfy the Schrödinger equation. Corresponding to the ith particle. That's what I mean by single particle states. Okay? Now, how are we going to describe this many particle state of the system? One way of describing it is using occupation number formalism. So you can specify the state, many particle state, by specifying the number of particles in a specific state. In other words, here is the many particle state. And one particles in state 1, and 2 particles in state 2, etc. Okay? That's the occupation number formalism. you can reformulate your problem in terms of these numbers. Because if you want to concentrate on a physical property, it is going to come from contributions of occupied states. Empty states will not give you anything, isn't it? Imagine the solution of the hydrogen problem. There are many states available to one electron, but it occupies only one state, isn't it? Ground state, usually, and you can excite it to excited states. At low temperatures, you can take a view that it is a two-particle state. It can be excited at most to the first excited state, isn't it? So that's our picture. So we have an I particles in state with energy EI, or epsilon I. Okay? That's important. So Ni particles in eigenstate epsilon I. That's our occupation number formalism. And of course, if you add up all the particles in different states, it has to be equal to the number of particles at hand in the system. And if you want to get the total energy of your system, you have to find the individual energies per particle, multiply it with the number of particles, sum overall possibilities, occupied levels, of course, you get the total energy. Now, what are these particles? What can be these particles? This could be classical particles or quantum particles like fermions and bosons. Now, do you know the difference between fermions and bosons? Kind of. Not too strongly, but kind of. Let's concentrate on fermions and bosons and their wave functions especially. What type of a wave function can describe a system of fermions and bosons? Okay? What is the specific form and why? Let's discuss that problem. Now, you can group these quantum particles into two, fermions and bosons. Let's consider as an example, simple example, consider two particles. Or two particle states, okay? So that the system has a wave function which is a function of positions of these two particles, okay, in the coordinate representation. This is the position of the first particle, that is position of the second particle, okay? Now, let me introduce a permutation operator that interchanges the particles, okay? Permutation operator. Well, you know these, but I'm helping you to recall what you have done before in your undergraduate study, okay? Permutation operator takes one, interchange particles, okay? Well, if you have a wave function like that, it takes it to psi R2, R1. It interchanges particles, takes one into two, okay? Now, if you apply once more, of course, you have to get back the original state. That means interchange once more, you get psi R1, R2. So what does that mean? It means p squared must be kind of a unit operator, must be 1. If p squared is 1, p can be plus or minus 1, isn't it? So that's important. This means p is plus or minus 1. If p is plus 1, this means when you operate with an interchange, the permutation operator, interchanging the particles, you get back the same wave function, isn't it? We call these bosons. Those who are having this property are called bosons. If p is minus 1, that means when you interchange two particles, you get a negative of the wave function. Then you have fermions. Well, why is this? Because fermions have a property where they can double occupy a state. You cannot put two fermions into the same state, isn't it? Exclusion principle. Huh? So let's check that. If you put two particles into the same state, if you apply with the permutation operator, you get back the wave function, which is itself. This is only possible if the function is 0. So this state has 0 probability. That's why we associate the state with -1, who changes sign under permutation, with fermions. It is in line with the exclusion principle. Okay? You cannot put two particles into the same state if they have this property under permutation. Okay? So you have to have a very clear understanding of the form of the wave function for fermions and bosons. We call one symmetric, we call the second one antisymmetric. So fermions have anti-symmetric wave functions, bosons have symmetric wave functions. One important property. And for fermions, we can only have 0 or 1 particle in a state. For bosons, we have any number of particles in the state. Okay, you can put any number. But what determines a particle to be a fermion or boson? What is the important property? Do you know? Well, it is their spin, isn't it? Particles with half-integer spins are fermions, particles with integer spin are bosons. So, fermion or boson depends on the spin. Spin determines the statistics, in other words. There is a deep relationship between spin of the particle and the statistics they obey. If the spin is half integer, like electron, proton, or neutron, these are spin 1/2 particles. They are fermions. And photons with spin 1 and mesons with spin 0, these are bosons. There are some fundamental particles with half-integer spins and integer spins. There are also composite particles, where like atoms, okay, which is a collection of in an atom you have nuclei and electrons. So if you have an even number of electrons, you have a boson. An odd number of electrons, you have a fermion. For example, helium-3 is a fermion. Helium-4 is a boson, isn't it? Total spin is going to come from quantum mechanical combination of spins. Up and down will cancel each other. If you have odd number of electrons in an atom, you have an unpaired electron, so the spin is 1/2. If you have more, of course, it can be half integer. If it is half integer, you are dealing with a fermionic system. Now, how are we going to write the wave function, total wave function for fermionic system and bosonic systems? Let's discuss a little bit that. We know the individual states. In terms of these, we can write the system wave function. What will be the form? Do you know for fermions? What is the form of the total wave function? You, of course, know, but you don't remember. I will remind you what it is. You have studied these before. I'm just repeating. Now, for bosons, here is the property for a boson. if you have a wave function for the system, let me interchange two particles, okay, Rj and Rk with positions Rj and Rk, and get the following function. What will be the sign in front of the wave function if they are bosons? Interchange two particles. Will the sign change? No, of course. If this is plus, you have bosons. Now, if you have fermions, in the fermionic case, if you do this interchange, you have to have a minus sign in front. It changes sign when you interchange two particles. Now, again, let's write everything in terms of single particle states. And I have written for you what I mean by that. Okay? Well, let's consider a complete state basis functions, state functions, so that we can expand our function, system wave function, in terms of these. Let's take them to be orthonormal. The system wave function can be written as follows. In terms of these functions, as a combination of these individual functions. And of course, for fermions, it has to take an anti-symmetric form. Do you remember any form which changes sign when you interchange two particles in physics? Determinants have this property, isn't it? If you have two columns of a determinant exactly equal, you have zero. And if you interchange the columns, you get minus the initial wave function. So for fermions, here's the way we write them. let me simplify it a little bit. Here is the way we write them in terms of individual single particle states. Well, it's simple to take them to be two-state example. For bosons, it has to be a simple multiplication of the wave functions, which doesn't change sign if you interchange the particles. So if you have two states, very simple example, here is the wave function for the system. Which is phi nu 1, R1, phi nu 2, R2, isn't it? That's the way you expand it. Multiply this to minus that. Minus phi nu 1, R2, phi nu 2, R1. What happens to this function if you interchange particles? If you take this, make the interchange here, mu1 R2, mu2 R1. Exactly this, isn't it? So it changes sign. It becomes minus the initial one, isn't it? Exactly the property we want. This is for fermions. And for bosons, of course, we have the symmetric combination, which is phi nu 1 R1, phi nu 2 R2, plus phi nu 1 R2, phi nu 2 R1. What happens here if you interchange particles? Look at this form. If R1 goes into R2, this phi R nu 1 R2, which is that term, nu 2 R1, which is the other term. This becomes nu 1 R1, which is that one. That becomes mu 2 R2, which is this one. So it doesn't change anything. Interchange of two particles doesn't change the sign of the wave function. This is a symmetric combination. That is an anti-symmetric combination, okay? The first one changes sign if you interchange particles. The second one doesn't do anything when you interchange particles. It doesn't change its sign. So this describes a bosonic system. That describes a fermionic system. These are the most important things you should keep in mind. Of course, to normalize them, you have to multiply this by 1/2 factorial for two particle system. For an n particle system, then the most general way of writing this is the following. I have written for fermions a determinant, usually called Slater determinant. Here is the general form. The wave function. Number of particles, n particles, or the kth state, 1 over square root n factorial, normalizing function, delta p, p, and u k1, 1, u k2, 2, etc. You just permute all possible permutations. This delta p is plus or minus 1 to the power order of permutation. This is order of permutation. So if you interchange two particles once, and if you do it once more, interchange them into each other once more, you get back the same function in the fermionic case, even in that case. So what is the order of permutation is important. Are you doing it once, twice, or 3 times is extremely important. So, plus is for bosons and minus is for fermions. If under these operations the wave function doesn't change its sign, you are dealing with bosons. If it changes sign for odd number of permutations, then you are dealing with fermions. Okay? You can now write, using this general form, the total wave function for 2 particles, 3 particles, or 4 particles. Why don't you write for 3 particles yourself? Let's see what will be the total wave function. Now, what I want to do now is to use this property of the system, fermionic or bosonic system, to study that system and try to get some information about these occupation numbers. What is the average occupation number for fermions and for bosons? Average occupation number. How many particles do we have in a state? We know in fermionic systems it is either empty or 1 particle. For bosonic systems we can put any number in. But what is the average value? Do you know the answer to this question? Huh? You know, of course, but you don't remember. Let's do it. Now the trick I'm going to use, I will choose my system as a subsystem of the whole thing. Okay? Let me choose a subsystem. Let me specify my system first. I'm going to apply, I told you something about grand canonical ensemble. Do you remember? I said, you see its power when you are dealing with quantum particles, quantum systems. Let's consider a system. I will define the system as follows. our system, for which I'm going to use the concept of grand canonical ensemble, which is the grand potential and everything, or Q potential, whatever you want to use. Subsystem, this is subsystem with NK particles in state K. So the total energy of my system is NK EK, and total number of particles is the total number of particles in that specific state. Okay? Is this clear? That's our system, which is the subsystem of the total. Well, if this is chosen like this, the probability of having NK particles in this case state in grand canonical ensemble is following: minus beta NK EK minus NK times mu divided by the grand canonical partition function. This grand canonical partition function is for your system, that is the subsystem. Why I am doing this? Why I am choosing grand canonical ensemble? Because in quantum systems, remember, the particles may be leaving or entering the state. You can excite them to higher lying states, or they can drop down to empty states. So the particle number will not be kept constant in those states. So if the particle number is not constant, is variable, then normally it is the grand canonical ensemble, isn't it? So that's why I'm choosing the grand canonical ensemble. And it is easy to do this calculation in that ensemble, as I'm going to show you. Now let's concentrate on this system and write the grand canonical partition function for that specific thing, which is NK e to the minus beta EK minus mu times NK, isn't it? Oh. Because for total energy, you have to multiply EK by NK and mu by NK. So that means the whole thing to the power NK. So once more, this occupation numbers can be 0 and 1 for fermions, 0, 1, 2, whatever, infinity for bosons. You can put any number of particles in a bosonic system to any one particle state. Now, you can either use Q potential, or omega, which is the ground potential. I will use omega this time, because its derivatives are quite simple. Omega was equal to P times V, let's use the ground potential. Okay, ground potential. And that will be KBT ln of the partition function, or KBT ln of, well, this sum I have written over nk e to the minus beta ek minus mu to the power nk. Now we can calculate that sum quite easily, okay? Instead of our system, which is the subsystem, if you want to think about the whole system, here's what we should do. If you want to write the ground canonical partition function for the whole system, we have to multiply these individual ground canonical partition functions. And if you want to get the ground potential for the system, we have to sum them. Let's concentrate on fermions and get the average I want, okay? What is this for fermions? This sum has only two terms, isn't it? Nk can be 0. If nk is 0, this is 1. If it is 1, that's the exponential. Very simple, isn't it? So for fermions, let's do it before we finish. The sum has the following. This is our partition function now. I'm doing 1 for nk 0 plus e to the minus beta ek minus mu. Isn't it? Two terms in the sum. And if we go to average or mean number of particles in a state, in the state we are considering single particle state K, it is nk average. We can relate that to the derivative of the ground potential with respect to mu. I have done this before, so check it at T constant temperature and volume. If you do this, you have the following. KBT is constant, 1 over the function, derivative of the function, beta comes down, e to the minus beta, ek minus mu. Beta cancels KBT, isn't it? Beta is 1 over KBT. So you have the following, e to the minus beta epsilon k minus mu divided by 1 minus e to the minus beta epsilon k minus mu. If you take into minus parentheses, minus exponential parentheses, you can cancel numerator with that parentheses, and you get the following: 1 over e to the beta positive now minus 1. Have you seen this before? Huh? It is Fermi-Dirac distribution function. So Fermi-Dirac distribution function is nothing but the average number of particles in a single particle state, isn't it? That's Fermi-Dirac distribution function. So, you are familiar with the function, but you don't know what it means. So, I think you will remember now everything. Thank you. I will continue with Bose distribution, Bose-Einstein distribution in the coming hour.